Next up, let's talk about heat exchange. So we talked about work, we talked about the overall energy exchange. Now let's get into heat exchange, Q. Heat is the exchange of thermal energy between the system and surroundings. So heat exchange only occurs when we have a temperature difference, and temperature is a measure of the thermal energy within a sample of matter. We are going to use degrees Celsius a lot, sometimes Kelvin, but heat flow is going to be able to match that temperature idea. Heat flowing from matter with a high temperature to matter with a low temperature usually occurs. So if you think about pulling an ice cube out of the refrigerator and bringing it to room temperature, what happens? The cold ice cube eventually matches the temperature of the warm room and they reach a thermal equilibrium. So we'll be talking about thermal equilibrium a lot and utilizing that idea in terms of that energy is not lost in a reaction. Energy can be transferred, but energy has to be constant. And that's really what makes thermal equilibrium occur. How are we going to quantify this? With something called heat capacity, C. Capital C is how we abbreviate heat capacity, and it is the quantity of heat absorbed in when a temperature increases. And every single bit of matter, every different piece of an object or every different molecule has a unique heat capacity. Heat capacity is going to be able to tell us how does the temperature change when we apply a certain amount of thermal energy or remove a certain amount of thermal energy. It's the conversion factor between Q and temperature. Specifically looking here, Q, heat, is equal to the heat capacity times the change in temperature. Units of C are usually joules per degree Celsius or joules per Kelvin. So be aware that either temperature Kelvin or degree Celsius can be used. Again, we'll most likely be sticking with degrees Celsius. The larger the heat capacity of the object, the smaller the temperature will rise, because look at the units here. The units are per degree Celsius. So as the heat capacity increases, that denominator should be getting smaller and smaller and smaller. So thinking about a molecule with a heat capacity of 4 versus that of 1, the heat capacity of 1 means that the temperature will fluctuate rapidly with little energy. It only takes 1 joule to move it 1 degree Celsius, versus a heat capacity of 4 means it takes 4 joules to move the temperature 1 degree Celsius. So factors that could affect the heat capacity. Why do some things have higher and some things have lower? It depends on the amount of matter. It usually is measured by its mass. So 200 grams of water requires twice as much heat to raise it 1 degree Celsius than 100 grams of water does. The heat capacity of an object depends on the type of material as well. So sand versus water, 2 different compounds, 2 different interactions with heat, because there are different bonds. And so we see that things like sand have a much lower heat capacity than that of water. Heat capacity of an object is proportional to its mass and the specific heat of the material. Specific heat is what we will most likely be utilizing quite a bit in this class. And the reason for that, using specific heat rather than the heat capacity, is because the specific heat is normalized to include mass in its units. And so that way it's not dependent on mass like heat capacity is. So the specific heat of a material is abbreviated big C, little s. And this is going to be in units as we see at the bottom. I'm just going to rewrite them. Joules per gram degree Celsius. And that is a much better tool for us with laboratory instrumentation, laboratory use, because we can have any starting material of mass and be able to use a heat capacity and be able to use the specific heat capacity, not just the plain old heat capacity. So the quantity of heat absorbed by an object can be determined if we know the following: the mass of the sample, the specific heat capacity, and the temperature change. We're going to be using this calculation a lot in calorimetry and understanding heat exchanges in reactions. Specific heat capacity is a measure of a substance's intrinsic ability to absorb heat. It is still the same idea as the amount of heat required to raise a substance by a degree Celsius. However, now it's the ability of the heat to raise the temperature by 1 gram of a substance by 1 degree Celsius. So it includes mass. There are such things as molar heat capacities as well. This is used in other areas of chemistry because it's dealing with 1 mole instead of 1 gram. So it's more looking on the atomic level rather than the macroscopic laboratory scale. The molar heat capacity is joules per mole degree Celsius. So heat transfer, when we think about heat transfer, we're talking about, let's take something hot or cold and drop it into something that is a different temperature and measure the thermal equilibrium. So when 2 objects at different temperatures are placed in contact with each other, heat is going to flow from the material that is hot to the material that is cold. And heat will flow until both materials reach that same final temperature, and that is thermal equilibrium. The amount of heat lost by the one object, by the hot material, is going to equal the amount of heat gained by the cold material. So Q of, let's say, one hot object is going to equal the negative Q of the cold object, or vice versa. The negative sign can be anywhere, as long as one has the negative and one has a positive sign. You can also write system to surroundings here. Lots of different subscripts that we can utilize, but what this is really helpful for is understanding and calculating, quantifying the flow, and even quantifying the final temperature, or quantifying the mass of an unknown amount of substance in this relationship. Overall, by understanding the Q of the system is equal to the negative Q of the surroundings, we can utilize the mass times the specific heat capacity times the change in temperature of one is equal to the negative times the mass times the specific heat capacity times the change in temperature of the other. So looking at this setup, this image from your textbook, a block of metal at 55 degrees Celsius is added to water at 25 degrees Celsius. The metal is hot, the water is cooler, I'll just say cold just to differentiate. So heat will be flowing out of the metal into the water. The water will gain the heat, the metal will lose the heat until thermal equilibrium is reached. Let's do a practice problem. You find a penny. Minted before 1982, pennies were actually made nearly of pure copper. Nowadays, they're made mainly with zinc and then copper plated. We got cheap. So let's talk about how much heat is absorbed by a penny if it warms from the temperature of snow, which is about -8 degrees Celsius, to the temperature of your hand, right? So let's just, woo. This is why my parents said, don't be an artist. Penny, 1 cent, go be a chemist instead. So the copper penny is very, very cold. All right, the copper penny starts, I like writing everything out. Temperature initial is -8 degrees Celsius. Temperature final is 37 degrees Celsius. The mass is 3.10 grams, And the specific heat capacity we can get from table 9.2 in the textbook or on the previous slide, which is 0.385 joules per gram degrees Celsius, specifically for copper. Now, Q of the penny is equal to 3.10 grams times 0.385 joules per gram degrees Celsius times final minus initial. Again, with these state functions, be very aware that we need to have the proper setup for our overall energy exchange, right? If we don't set up the change in temperature correctly, we will not have the correct energy exchange. So Q for the copper penny is going to be equal to 53.7 joules. All right. First step, let's just look at sig figs here. 37.8 minus a negative 8.0 is 37.0 plus 8.0. That is 45.0 degrees Celsius. 1 decimal place and a 1 decimal place gives us a reporting answer in that addition as 1 decimal place. Then we'll look and we'll say 3 sig figs and 3 sig figs. Specific heats you can utilize here, they're all going to be 2 decimal places, so I would rather not look at that for a sig fig. Think of this as a unit conversion factor. That's really what it is. It's a conversion factor between mass, temperature, and energy units of joules. So I'm going to report, again, 3 sig figs. Now, positive, what does that mean? Heat is entering the penny. Heat is being absorbed by the penny. That's how its temperature is increasing. So the exchange of energy, we saw this slide already. I just brought it back up again to include the idea of now quantifying heat and work. The exchange between a system and its surroundings can either be the exchange of heat energy, Q, or the exchange of work, W. All right, so they can include one or the other or both. Now, measuring delta E. In a calorimetry experiment, we can either do one of 2 things, calorimetry with constant volume or calorimetry with constant pressure. We're going to talk right now about constant volume. What does that mean? Rigid volume. Think about being enclosed in a solid system, okay? No work is done at constant volume. The delta or the change in volume would be 0. So W would be 0. Okay, so at constant volume, we are talking about energy of the system directly being related to the Q of the system. In practice, temperature changes of individual chemicals involve the reaction that cannot be observed directly. So instead, the temperature change of the surroundings is measured. We can't take a thermometer and actually go straight into a system like a molecule or a bond or anything like that. So what we will be using in measuring or quantifying this change of energy in calorimetry is by measuring the surroundings. Surroundings are going to typically be water, and that is controlled in constant volume calorimetry. We will be using an insulated type container for all of our calorimetry experiments. The first one that we're going to talk about is bomb calorimetry. Bomb calorimetry kind of sounds scary. The only thing that's scary about it is that it's rigid walls. It's kind of like a pressure cooker. If you've ever seen a pressure cooker before or used a pressure cooker, it's a solid container. You can put stuff in it and then close it up, seal it, and say go. All right, so when we do the bomb calorimetry experiment, which we'll see in just a second, the setup, bomb calorimetry is constant volume calorimetry. Now, bomb calorimetry is actually one of the main ways of how we determine caloric energy, right? So talking about food, calories, which is really cool because in our bodies, we ourselves are essentially breaking and making bonds. We take food inside of us and we break it up and get energy from that food, right? And so bomb calorimetry is a great way of breaking up certain compounds like sugars or fats or things like that, and actually measuring the amount of energy held within that molecule, and therefore being able to slap a label on a packet of chips or a box of cookies. Again, Q of the surroundings is what we are going to be measuring. That is what we call the Q of the calorimeter. And then that will be equal to the opposite sign, Q for the system. This is a bomb calorimeter. To measure delta E, because of constant volume system, we have to use a rigid solid container inside of a closed system. So here, right here is the water. This is what we are calling the surroundings. Tightly sealed inside of that is the reaction flask. This is what we call the bomb, but inside of it is just a sample and oxygen. Most often what we do in bomb calorimetry is oxidation reactions. And so we'll put a tiny little bit of sample hovered right there in the middle. We'll take all of the air out of it and only pump in oxygen. The thermometer up here is only measuring that of the water, measuring the surroundings change in temperature. We have an ignition wire because, again, we are going to be doing a combustion reaction. Some sort of hydrocarbon or fuel sample is placed in a bomb with oxygen. We combust it. We have that ignition wire to start the actual combustion reaction. And then heat is going to be exothermic out of that system, and that exchange of heat is going to be read by the thermometer of the surroundings. We have a stir to make sure that all the molecules of water are stirred thoroughly and the heat is evenly distributed so that we can read the temperature change appropriately. The heat capacity that we will be using for this is going to be based off of the calorimeter. So technically, it's a calorimeter constant, a C-cal, and its units are usually kilojoules per degree Celsius. Why do we not need the mass here? And the reason is because there is a specific amount of volume of water encased in this. When you get a bomb calorimeter from a scientific laboratory distributor, it usually comes already standardized. And that means it knows the amount of water that is encased there, so it knows the mass of the water, so it incorporates it already with the calorimeter constant. And so there's specific instructions in setup. Y'all don't need to know that. What you do need to know is how to actually work through the problem. So here's an example. Here's our sample, 1.01 grams of sucrose. This is our sample, which is going to be the system. We don't need this yet because remember, bomb calorimetry measures the surroundings. It's going to undergo combustion in a bomb calorimeter. The temperature of the surroundings, remember, rises from 24.92 to 28.33 degrees Celsius. Find the delta E for the reaction of the combustion of sucrose in kilojoules per mole. All right, the heat capacity of the bomb calorimeter was determined in a separate experiment. Our C-cal is 4.90 kilojoules per degree Celsius. You can ignore the heat capacity of such a small sample of sucrose because it's negligible compared to that of the heat capacity of the calorimeter. We are also simply just measuring the Q of the calorimeter utilizing C-cal times the delta T. The Q of the calorimeter will equal the same magnitude but opposite sign of the reaction. And then to get the delta E of that reaction, the only difference between Q of the reaction and delta E are the units. We do have to divide by moles of sucrose that we will be utilizing in this reaction. All right, so it's just that little extra one last step. So first step, let's calculate Q of the calorimeter. Q of the calorimeter is going to be 4.90. Remember our units, it's given, but it's important to just identify them. 4.90 kilojoules per degree Celsius. Final minus initial for our temperature. Again, the setup of that degree temperature is important. Final minus initial so that we get the right sign for QCal. So just side note, 3.41 degrees Celsius, that's 3 sig figs. I'm going to multiply it by 4.90, 3 sig figs, 16.7 kilojoules of heat absorbed by the calorimeter. This is positive, which means in step number 2, Q of the reaction is a negative 16.7 kilojoules. The reaction itself released the 16.7 kilojoules to the surroundings. So final step, we want to be able to take that Q over moles, okay? You don't need the negative here if you already switched the sign, so I don't want to confuse anyone. But we have that negative 16.7 kilojoules over the moles. How do we find the moles? This is where we need to go back to the amount of sucrose that we had in the sample. So step number 3 is going to be calculating the moles. 1.010 grams of sucrose times 1 mole over the molar mass, 342.34 grams. We're getting 0.00295 moles. That many moles is going to become our denominator. Usually in bomb calorimetry, in these combustion reactions, we get very, very large exothermic delta E's. Negative 5,661 kilojoules per mole. To keep this into 3 sig figs, you can either do one of two things. You can change that to a 0 and say 5,660, because that final 0 without a decimal place means that it is negligible, doesn't count towards sig figs, or you can change this to scientific notation, which I tend to want to do just because seeing that 0 kind of gives me the heebie-jeebies. Negative exothermic 500 or 5.66 times 10 to the 3 kilojoules per mole.